Okay, that's topic one. Here's one of the questions that came up a lot. What resources would you recommend for beginning calculus instructors, and not just beginning calculus instructors, but what resources would you recommend? So here's a couple of things I would suggest. The very first thing I'd suggest is that you go to AP Central, and there's the website. Follow the links in there to the home page for A, B, AP Calc, or BC. And there is just a ton of material there. There's a topic called Essential Course Resources. There's a topic called Classroom Resources. There are curriculum modules. There are special focus material documents. The special focus material documents, there's a new topic written once every couple of years. And in fact, I edited the last one, which was all about approximation. The special focus material is generally given out at the College Board workshops for the next 2 or 3 years. And so if you attended a CB workshop, you probably got a copy of the approximation booklet. There's another topic from your AP colleagues. That's lots of material under that. And people always ask me, well, where can I get some sample exams? Well, if you don't know, the international exam is released every year to audit teachers. So I think you'll remember, those of you who have been teaching AP Calculus for a while, I believe it was the 2008 exam was released. There are no plans that I know of from ETS or the College Board to release another exam in that same manner. However, the international exam will continue to be released to audit-approved teachers. So there are at least 3 international exams that audit teachers can get a hold of. And as far as I know, that practice is going to continue. Now, when you download the curriculum framework, I think there's something in there about this, but I'll let you know anyway. There are some pacing guides being developed. There'll be 3 or 4 of those that will be available soon. And there will be a practice exam. I don't think that's plural, but there's a practice exam that will be released very soon too. I think either late this summer or early fall. Okay. The third question I want to address is common topics. I got a lot of these about, well, what are the most common topics on the AP Calculus exam? And so what I'm going to do is to try to talk about these common topics as I see it. I've actually gone through a lot of exams and been involved with AP Calculus for over 25 years. So I'm going to tell you what I think the common topics are. I'm going to give you some examples of those from the free response questions, and I'm going to show you how we graded some of them. And Nicole, if you're still there, this may, I think, start a couple of more questions from participants, okay?
Okay, I'm still here. We've only gotten a couple of questions on, and you're going to be sharing the slides, so I didn't want to interrupt you. A couple people were saying they were taking a lot of notes, and they wanted to know if you'd be sending these slides out.
I would be happy to give these to you, sure. Absolutely.
Perfect. There you go. Otherwise, continue to send. No one's really chatted me in the past few minutes, so if you do have a question, you can send me a question using the chat function. Thanks.
Okay, thanks. So look, in the past, the AP Calculus exam, I think, was very predictable. And, you know, this used to be a common complaint. I remember about 10 or 15 years ago hearing somebody tell me, well, you know, we used to always give this question where we give students a polynomial, and the very first thing we'd ask them to do is find the roots of that polynomial. Now, that's not really a calculus question, but the answer always was 0, plus or minus 1, 2, 3, or 5. And so it was very predictable. We always asked them about the analysis of a function. We always asked them about particle motion, something about velocity and acceleration. And there was always an area of volume question that involved a polynomial or a trig function. It was very predictable. But once calculus reform started a little over 20 years ago, things changed. Now we have a wide variety of applications. We have lots of problems and context. I can tell you that having served on the development committee, this is actually one of the most enjoyable parts, is to try to write problems in context. We've had problems, if you haven't seen these problems before, we've had problems about amusement park rides, snow falling in our driveway, and just as an aside, that was an extremely difficult problem to correct, to grade. And last year we had a problem on grass clippings. We've recently had problems that have involved piecewise defined functions. We never used to see those, but now we do. And we have loads of problems that involve functions defined by an integral. So things have changed.
Really quick.
Sure.
A question just came through. This is from the last section, but from Julie, where can we find the released international exams?
The released international exams are only available to AP Calculus teachers who have submitted their syllabus for audit and have been approved. Now, I don't do that, but I understand that if you've done that, you have a special way to log in to this ETS site. And once you do that, that international exam will be available to you.
Thank you.
Okay?
Yep.
So the first topic, the first common topic or theme, I think, in pre-response questions is continuity. So we want students to be able to determine whether a function is continuous at a specific value. And often in these questions, very often in these questions, we have a piecewise defined function that we want the students to work with. Now, my experience suggests here that students have very good intuition about continuity. And you know that old phrase, when is a function continuous at a point, I can draw it across that point without lifting my pencil. And students have very good intuition about this. However, many students don't address all the parts of the definition. And you really need to do this mathematically when you're looking at continuity. So I just wanted to remind you of this definition. I won't do this for every one of these common items or themes. But remember that students need to know this definition. They need to know that a function is continuous at A if the following conditions are met. F of A must be defined, the limit has to exist, and the limit has to be equal to the value of the function at A. If any one of those conditions is not satisfied, then the student can stop right away. The function is discontinuous at A. So here's an example of one. In 2012, AB4 had a function like this in part C. Well, first we started with a function f of x. And then in part C, we defined a new function g that was piecewise defined. And we asked the student, is g continuous at x equal minus 3, sort of that break point. And we even told or asked the student to use the definition of continuity to explain your answer. So that's the only part that I'm going to focus in on right now. Here's what the standard looked like. We wanted the student to somehow look at the two one-sided limits at minus 3. We wanted them to get those limits. We wanted to conclude, since they are the same, the overall limit exists. We wanted them to check to see that the function was defined at minus 3, and finally conclude that the limit is equal to the value of the function at minus 3, and therefore the function is continuous there. Now, this part was worth 2 points, and I'd like to draw your attention to the first point, where it says considers one-sided limit. I think if I've done one thing as chief reader over the last several years, that is I'm trying to introduce, where possible, more conceptual points. And this is what I would call a conceptual point. What does it mean for the student to consider one-sided limits? Well, professional judgment often, but we want to see that the student knows that in order to check continuity for this function at minus 3, they're going to have to look at those two one-sided limits. Now, I'll admit when we graded this, when we scored this, we saw a lot of crazy notation for limits. I would encourage you to encourage your students to use proper notation. But if there was some indication that the student was addressing one-sided limits properly, we'd give it a point. And that everything else was wrapped up in that second point, the answer with the explanation. I have one note down at the bottom. I put this in here because it comes up frequently in mean value theorem problems and intermediate value theorem problems. The student is often told that a function is differentiable. And remember, the differentiability implies continuity, and sometimes they need that fact in order to solve the problem.
Two quick questions came through before we move
Sure.
on. The first one is actually a statement, not a question, from Brian G. He says that if you go to the AP audit site, navigate to secure documents, teachers should be able to see the 2012, 2013, and 2014 released exams as well as a practice exam. So there's another resource for you.
Excellent.
And then
Thank
another
you.
question from Eric S. And I'm going to preface this with saying I have never taken calculus in my life, so I will likely mispronounce something. But the question is, you guys have the craziest words. The question is, what forms of L'Hopital's rule will be added? Just quotients, exponential indeterminate forms, infinity minus infinity forms.
Hey, I'll answer that, but did you just say we have crazy language, Nicole?
You do, and this is coming from an English major. Your language is a lot harder.
That's an easy one to answer. So L'Hopital's rule in AD, it's just 0 over 0 and infinity over infinity. Now, the truth is you probably teach the other indeterminate forms, but those are the only two forms that will be explicitly tested, so that's an easy one. Okay?
Great, thank you. I'll let you know if any more come in.
Okay. So my second theme here is particle motion. There have been a lot of particle motion problems on the free response questions, and I think that this is going to continue. So here's a little bit about background. We're often given a function that would produce the position of a particle at a specific time. One common question associated with this is, what's the speed of the particle? Or is the speed increasing or decreasing at a time t equals t0? Sometimes we have to ask students, or sometimes students will have to examine the sign of the velocity and the acceleration. And that next line down there I'll address in a minute. I thought this was very clever, and this is, I think, a result of technology, at least in my opinion. If you want to know whether the speed is increasing or decreasing, you can actually look at the derivative of the absolute value of the velocity. Something that I would never have thought to do 20 years ago analytically, but with a calculator, they can actually do this. And another common question is the total distance traveled by the particle over a time interval. So I'm going to take a look at a couple of examples here. I didn't show you the question on this one, but this is from 2013 AB2. We actually asked the student to give us an expression for the position of the particle at any time t, and then we asked them for the actual position of the particle at time t equals 5. This was worth 2 points, 1 point for each of those lines. I can just tell you that some common mistakes here are not including that initial position of t, and I would also like to suggest that you encourage your students to use proper notation here and not just give us a stream of consciousness. Make sure that when they connect things with equal signs, those connected items are indeed equal. In past exams, looking at the bottom here, sometimes a question like this is worth 3 points. Sometimes we would ask a student for, let's say, we would give them some information and ask for the position of the particle at time t equals 5. If it were a graphing calculator active question, we might give them 1 point for setting up the correct or using the correct integrand, 1 point for the limits and the initial condition, and 1 point for putting it all together and getting the correct answer. Sometimes we give partial credit on a question like this, but if we do, we want to make sure that the lower bound and the initial condition must agree, and I think you understand what I mean by that. And we do pay attention to that dummy variable. If you look up in the first line of that solution, you know, we really don't want students to be using x's in both places. If we do, okay, between you and me, we usually let that slide. If this were a question where we would expect to see more, well, we'd want to see what the student did with that, with those two variables. But we'd really like to see a different variable inside the integral. Here's another example of a particle motion problem, especially part D. So we have an expression for velocity, and we want to know is the speed of the particle increasing or decreasing at time t equals 4. And there's that phrase, give a reason for your answer. Here's what the standard looked like. 2 points for the conclusion with the reason. We expected that students would look at the velocity at 4 and the acceleration at 4. Notice that both of those were less than 0 and conclude the speed is increasing because the velocity and the acceleration have the same sign. Now let me make a couple of comments about this. We didn't ask the student to tell us what V of 4 and A of 4 were. So the truth is that they don't have to. They could just say V of 4 is less than 0, A of 4 is less than 0. And therefore, since they have the same sign, the speed is increasing. The issue is if they decide to give us values, then the values they give us must be correct up to 3 decimal places, rounded or truncated. So if the student is going to give us a value, for V of 4, for example, it's got to be correct to 3 decimal places, rounded or truncated. Anything beyond that 3rd decimal place, we're not going to look at. They could give us minus 11.4. Fine. Minus 11.47. That's okay. Minus 11.476. That's okay. If they give us a value, it has to be correct. There's a minimum that's sort of necessary for 2 points here. We go through what's called a 5-day pre-reading prior to all the readers getting there. And we talk about sort of what is the minimum acceptable response. And the minimum acceptable response is something like the following. V of 4 less than 0, A of 4 less than 0. Therefore, the speed is increasing at time t equals 4. Done. We'd certainly like to see more, and usually that minimal response is very contingent upon seeing it on the paper, seeing exactly what it looks like. We would encourage students to write out a little bit more, but there is sort of this line in the sand, and I want you to know that. Another way that a student could get full credit for this is to take a look at the derivative of the absolute value of the velocity at t equals 4. This is one of those operations that we allow on a graphing calculator. I think that's the correct answer in this case, 22.296. The derivative is positive, therefore the speed is increasing at time t equals 4. That's very clever. It's a very clever way to use the graphing calculator and a way to answer this question, again, that I wouldn't have thought of, say, 20 years ago. Here's one more from 2011, AB1. We have the velocity and the acceleration of this particle. And in part C, we want the total distance traveled by this particle from t equals 0 to t equals 6. Well, we would expect the student to give us an expression, integral 0 to 6, absolute value, V of t dt, plug that into their calculator and get an answer at 12.573. 1 point for the integral, 1 point for the answer. We have an expression, or we have a whole list of terms and conventions at the reading, and one of them is a bald answer. Some of our students, some of your students are so good at problems like this, they can maybe just read part C and say, oh, I know what I need to do. Plug it into their calculator, get an answer, and just write down 12.573. That's not enough. The student has to write a mathematical expression telling us where that 12.573 came from. It has to be done using correct mathematics. It cannot be done using calculator technology, for example, FINT. So bald answers rarely, if ever, will get full credit. They may get some partial credit, but bald answers will rarely get full credit without any supporting work. Great. The next theme is accumulation. And these are just some examples of what I think of when I consider accumulation. I think of what I call this area so far function, which is sort of accumulating area underneath the curve from A to X. And suppose we were given a rate function R of t. We might ask the student to find a net change in the quantity over an interval. We might ask students to interpret expressions like this, the integral from a to b of r of t dt. We might ask them to interpret 1 divided by b minus a, the integral from a to b r of t dt. And if you're looking for good examples of questions that involve accumulation, we've had one on gravel recently. We've had tons of questions where we have water and tank everywhere, water being pumped in, water being pumped out. We had a question a while ago about that involved people entering an auditorium. We had a question involving profit. Remember the mighty cable company? I think that was the name of the company in the question. And we even had one involving snow on the driveway with a piecewise defined function that had 3 pieces. So I'm going to take a look at this gravel question. This is from 2013, AV1, BC1. We have gravel arriving at this plant, and it's modeled by that function capital G, and I'm going to look at part D, where we want the total amount of unprocessed gravel that arrives at the plant during the hours of operation. And in part D, we want the maximum amount of unprocessed gravel at the plant during the hours of operation, and justify your answer. Well, here's part B. You've already seen something like this before. We'd expect the student to set up a definite integral, tell us what that definite integral is, and yes, they can absolutely use the name of the function. We named it capital G of t, and I would recommend that students use the name if we gave it one. If the students try to write down the actual function, frequently they make mistakes with parentheses, and that can lead to points off. We expect them to give us that definite integral and plug that into their calculator and get an answer. And in part D, on the right-hand side, you'll notice that there's sort of a conceptual point here. We want them to somehow know that they need to set some derivative equal to 0. 1 point for the answer and 1 point for the justification. If you've been looking at the free response questions over the last 3 years, I happen to like solving these types of questions by setting up an appropriate table and picking, say, the largest or the smallest out of there, whatever we need. I understand that there are different ways to solve this problem, and that we are certainly sensitive to that. We award credit for good calculus work, but I think this is a very systematic, tried, true way to get the answer to this type of problem. So 1 point for the answer, 1 point for the justification. What's the justification in this sort of an answer on the left-hand side? Well, the justification would be that table. But I looked at those 3 values, and I was able to pick out the maximum out of those 3 values of A of t. I think this is a very good problem that illustrates this idea of accumulation.
I do have one question, or 2 questions that came in the last minute. So the first is from Jeremy R. He says that our school has accepted a lot more international students than in the past. The teaching AP calculus has changed. One major problem is the language barrier. How is the language barrier taken into account on the AP exam when justifying or explaining an answer?
Well, I'll try to answer that in 2 different ways. Okay, first of all, we certainly do take into consideration contextual problems. We don't want to write a problem that's going to be foreign, just going to be crazy. No one would ever hear of it, if you were only living in the United States. So we're very sensitive to that when we write contextual problems. We want to make sure that students understand what we're talking about. The second part of that, how do we grade, how do we score responses where a student has to write an answer? We're very sensitive to that. We read everything very carefully. Sometimes that takes a long time. However, we are also sensitive to students making mistakes, especially with things like prepositions. If a student says something in their communication that is wrong, we have to take off a point for it. So we do read all of these explanations very carefully. We're sensitive to the language barrier, but if there's something mathematically incorrect, we do take off for it. Was there another question, Nicole?
There was. This one is from Ashley R. and she asks if a student labels an equation wrong, say S parentheses S, when it is supposed to be V parentheses T, but all of the mathematics is correct, could they still get full credit?
Tough question to answer without seeing it in context. Let me try to elaborate a little bit more on what I said a minute ago. If we have named a function, we suggest very strongly that the student use that name, say, in all of their calculations, say in a definite integral. If they don't choose to use the name and they choose to write out the function, that can lead to errors. Here's the most common example. Suppose a student writes out the function as an integrand and forgets a parentheses or puts a parentheses in the wrong place. And that placement or omission would lead to a different answer, a different numerical answer. We cannot give them credit for that setup. Now, we've sort of adopted this convention that we will read with the student to see if they got the correct answer, our answer. But if they have presented it incorrectly, they tend to lose a point. Now, if you're talking about parentheses in something like G of T or V of T, well, we're willing to usually overlook something like that, as long as it's not clear the student is trying to multiply or anything like that. So that's the best answer I can give you without seeing something in actual context. But presentation is very important. I think, this addresses that idea of notational fluency. We need students to write succinct, correct mathematics. Okay, integral approximation. This has been a very big part of the pre-response question. And in fact, I think I mentioned earlier that approximation was a special focus material or was a special focus booklet a couple of years ago, still being used. We need students to be able to use and understand left, right, midpoint sums, trapezoidal sums. I know that many of you teach Simpson's sum using Simpson's rule or Simpson's sum, but we don't ask any questions about that. It's fine that you do that, but we're not going to ask a question about it. Lots of tabular data type questions. Be careful. Many of the tabular data type questions have used unequal subintervals recently, where we understand that there are calculator programs out there that deal with equal subinterval. We often ask students to interpret one of these approximations, and we often ask them, is your answer an overestimate or an underestimate, and why? So here's an example. This is a typical one. This is from 2012, AB1, BC1. We have a table of values up there, W at specific values of time, and I'm going to focus in on part C, where we're telling the student the average temperature of the water is given by that expression. Use a left Riemann sum to approximate that expression, and then does the approximation over or underestimate the average temperature of the water. Up at the top, here's what the standards look like. And I want to talk much more about this. 1 point for a conceptual point here for understanding what the left Riemann sum looks like. 1 point for the approximation, that's that value, 60.79. And then 1 point for telling us that it is an underestimate and giving us the reason why. Now let me try to go back and forth between the notes down at the bottom and the solution up at the top. The very first line in that solution, where it starts out with 1/20th and 4 times W of 0, that first line right there would get the left Riemann sum point. The student has demonstrated to us that they understand how to form a left Riemann sum in the context of this problem. The second line in that solution, if the student just wrote that second line in that solution, they would get the first and the second point. They've demonstrated they understand a left Riemann sum, and remember that students do not need to simplify a numerical result. So just that second line would get the first 2 points. If a student were to go on and make an error and somehow came up with 61.79, they would not get that approximation point. So down at the bottom here, we ask students to interpret, sometimes we ask them to interpret a definite integral like this. What we're looking for here, remember, are a couple of things, and we want students to tell us the units associated with their approximation. And if it involves a definite integral, we want to make sure that they're telling us that this approximation applies to an interval, not a specific value. I've already talked about simplification, and if you want to see another problem very similar to this one, look at last year's exam. AB4, BC4 dealt with two trains, and it had a problem very similar to something like this. Very typical.
A question came in.
Okay, go ahead.
I also wanted to give you a 10-minute warning. It's 6:20.
Okay,
and a question came in from Sarah S. She says that she's heard from past graders that when AP questions are graded, there's often a packet of information given for each problem that has more details about grading the problem. Is this a resource that could be shared with other teachers? Because it sounds like it could be very valuable, not for all teachers, not just for those that are at the reading.
Yeah, that's a very good question. Here's what happens at a briefing. All participants or all readers take lots and lots of notes on how the problem is going to be scored. The person making the presentation, the question leader, has prepared a packet of extra notes, notes about their briefing, special cases, what to do. Those notes go only to the table leaders. And the idea is that if a reader comes across a solution, a possible solution, they know it fits into some category that was discussed at the briefing, but they're not quite sure what to do. They go to the table leader and both consult this packet of notes. Unfortunately, that packet is not distributed. That packet is kept confidential. I don't know if I can tell you why. I don't know the answer to that, but I know that ETS does not want that packet of information being made public. There's nothing secret in there, but it's just very specific instances, how to grade certain things, and a summary of the briefing presentation.
And if I could do a quick plug for your past webinars, Steve has also done webinars with BFW describing in more detail all of the grading and common problems on the AP Calculus exams. Those are available on our website, and I will send out the links to you after the webinar, so you can view those, and that might give a little bit more background. I believe we have them for the 2014 exam and the 2013 exam. So we do have a couple more resources there for you.
Thanks.
Okay.
All right, next common item, next theme is functions defined by integrals. Here's an example up in the top bulleted item. Capital F of X is that definite integral. Be careful. Sometimes that X is a function of X in the bound. Sometimes the bounds are reversed so that the function is the lower bound. And sometimes there's even an added function like a polynomial. For example, 2x plus the integral from a to x f of t dt. Some common problems involving this function defined by an integral, well, find a function value, find several function values, for example, capital F of C. Compute a function value using the graph. Often the graph of f of t or f of c is given, f of x is given. And compute a slope of the graph at a specific value. We often ask about extreme values of this function capital F. Where is it increasing, decreasing? Where are the inflection points? Where is it concave up, concave down? This is an excellent example of a problem where we have a function defined by an integral. I'm going to take a look at all four parts here. So we have this graph of f on the right-hand side consisting of straight line segments and a semicircle. We want to find some values. We want to find whether g prime of minus 3, g prime double prime of minus 3 exists. We want to find the x-coordinate of each point of which there's a horizontal tangent. And we want to find all values where there's a point of inflection. Holy Toledo, this is a great question. Here's what the standard looked like. Well, we wanted the student to find g of 2 and g of minus 2, and we expected them to go to the graph to find these values. Basically, we're just looking for these two values. Please don't tell your students this, but we're usually in this kind of a problem looking for that minus 1/4. looking for the pi over 2 minus 3 halves. In some cases, they don't even have to be labeled as long as they're in the right order, but we'd really like to see some mathematical notation here. In B, we're looking for the answers, again, 2 and 1. We'd like to see the student make the initial connection that g prime of x is equal to f of x, but basically we're looking for those 2 answers. In part C, we're looking, again, for the connection that the student makes between g prime and f. There's a conceptual point on the right-hand side. We want to see the student considering g prime of x equals 0. We want them to identify x equal minus 1 and plus 1 as extreme possible places where there is an extreme value, and then 1 point for the answers with justification. If you look back at previous exams, we used to give a point for x equal minus 1 and the answer and the justification x equal 1. To the answer and justification. We feel that this way is a little bit gentler, more fair to the students, this way of grading. It's also a little bit easier to grade too, but I think it's fair. And down at the bottom, we want the students to tell us that g has a point of inflection at those 3 values, because g double prime is equal to f prime, and it changes sign at each of those values. That's very succinct. That's all we need to see. The student doesn't have to tell us it changes from negative to positive at each one of those places, just that it does indeed change sign. 1 point for the answer. The answer means those 3 values, and 1 point for the explanation. If you'd like to see another one like this, you can look at last year's exam, AB3, BC3. And let me take a quick look at volumes of solids with known cross-section. Area and volume problems have been very common on the exam. They've been in both calculator active sections and the analytic section. This is a really common problem. I went back and looked at previous exams, and all of those exams had an area volume problem. In questions where we ask students to find the volume of a solid with a known cross-section, it's usually, it has been in the past, either a square, an isosceles right triangle, or a semicircle. Now, look, if we get you one like this, could it change? Absolutely, but those have been, whoops, I'm sorry about those. Those have been the most common cross-section. We have not asked too often about a cross-section perpendicular to the y-axis, but we could. And often some of these questions say set up an expression for a certain volume or set up an expression to solve for a certain parameter, but don't evaluate. And here's one example of a volume problem or area problem. You may remember this one. This was a very difficult problem for us to score, to finally come up with a really good rubric. I think once we did, we were able to work through it. The region R is the base of a solid. For that solid, each cross-section perpendicular to the x-axis is a square. This is one of those where we're asking the students to set up an expression involving one or more integrals that gives the volume of that solid. So here it is. We would expect the student to somewhere on the paper find that point of intersection. For some reason here, many students, this was a graphing calculator active question, and for some reason, many students on this problem just assumed that x was equal to 4. Obviously incorrect. We're not sure why they did that. We wanted to see an expression like this for volume on this page, 2 points for the correct integrand, and 1 point for putting it all together and giving us an expression for total volume. Before I leave this one, let me just make a comment about that point of intersection. Remember that when students find a point of intersection that they're going to be using later on, they need to store that in that calculator to the greatest degree of accuracy allowed. They can report it on their paper to only 3 decimal places, but they need to store it to the greatest accuracy possible. My suggestion is whenever they do this, whenever a student does this, label it as a capital A, capital B, small a, small b. Label it, and you can use that label in your answer. It's okay for us to label functions. It's okay for the student to label functions and points like this or values like this. So remember, if they find a point of intersection, store it to a greater degree of accuracy, and it's okay to use labels. In this expression, there were 2 regions, and remember, sometimes we ask students to find some place where the regions are split into equal area. And we've talked about now this idea of a point of intersection in accuracy. Nicole, do I have time to do differential equations?
It's 6:29, so I'm going to leave that up to you. We still have about 53 people on, so.
Okay, why don't I do
people
differential
dropped
equations?
off, but.
Okay, we'll do DEs and we'll call it a night, okay?
Sounds good to me.
Okay, there have been lots of questions involving differential equations. In the past, this kind of a problem, this part, has been worth 5 or 6 points. Remind your students that the only way that we want them to know, the only solution technique we want them to know is separation of variables. So darn it, the first thing they should do is separate the variables. Don't forget that constant of integration. Sometimes students remember it but a little too late and add a constant of desperation that doesn't get them any points. And we'll see an example here where I'll address this issue. Do you really need the absolute value? Slope fields are easy. Sometimes we ask students on the free response portion to sketch a slope field. If they're trying to identify which differential equation goes with a slope field, look for straight line segments. Look for relative slopes, and again, if they're drawing a slope field, sketching a slope field and drawing segments, we look for relative slopes and grading that. Look for zeros of the differential equation. Those are easy. And in BC, sometimes we ask students to do or use Euler's method. So here's an example. This is from 2014 AD6. We have a differential equation there. We ask students to sketch a slope field here, sketch a particular solution in a slope field, and we ask them to solve a differential equation. Let me get through this. In part A, we wanted them to sketch a solution curve. If you think about it, this is a very difficult problem to grade. It's only worth 1 point. We were looking just for the general shape of the solution curve, subject to 2 constraints. We wanted it to go through 0, 1. That's the particular solution we were looking for. And we don't want this curve to go above y equals 3. As long as it looks something like that, the student got 1 point. Here's a solution to this differential equation. This one was worth 6 points, 1 point for correctly separating the variables, 2 points for getting the antiderivatives, 1 point for adding the constant of integration, 1 for using the initial condition, and finally 1 point for putting it all together and solving for y. I'm going to focus in on the box in the left-hand side in the middle. And the question is, do you really need that absolute value symbol? Well, yeah, the answer is you do really need that absolute value symbol. You don't know at this point what branch of the solution the particular solution is on. So yes, you do need that absolute value symbol. What if a student doesn't put it there? Well, the student could luck out. If indeed the particular solution that we're after is on the branch where that absolute value symbol is not necessary, they're okay. But if it's on a different branch, they absolutely need it. So I've tried to add in the last 3 years some explanation as to where that absolute value symbol went. And if you look at the last line in that box, because that particular solution yields to a positive expression inside that absolute value symbol, we don't need it. We're on the branch of the solution where the expression inside is positive. So down at the bottom here, maybe a little bit better explanation, the domain of a particular solution to a DE is the largest open interval containing the initial value on which the solution satisfies the DE. Some books call this, some people call this the interval of definition or the maximum interval of existence. So the solution to a differential equation, the solution to a particular solution, is on a domain, a maximum domain, containing that initial value. So that's why you need to worry about that absolute value. And that's why you can eventually drop it here in this case, because the solution is on a domain where the expression inside that absolute value is positive.